Okay, shall we start? Welcome back. Nice to see you again. Last time we were talking about managing visibility determination, mainly over an image-based approach, and have explained about the Z buffer and how in general in an image-based approach you are forced to add the buffer workaround, if you want, in order to decide problems which are global in their nature. One of such problems is, for example, is polygon A in front of polygon B in relation to the current position of the viewer? You cannot know that unless you use a buffer explicitly to store temporally the depth of each pixel you have calculated. So that's the reason why the Z buffer exists. You have support for the Z buffer also in OpenGL. You have native support. Did you try already activating the Z buffer in OpenGL? There's an exercise that Raffaella should make you do, in which you're going to draw a 3D shape. And you can see what's the difference in rendering this shape if you activate the Z buffer support in OpenGL or you do not activate it. So just have a check on that. That's okay. I think we can safely skip this. I mean, you can go through that. It's not very difficult. And still speaking about visibility determination, I have named several times bounding volumes. It has come the time to try and figure out how we can calculate these bounding volumes. Why do we want to calculate bounding volumes? Because when we want to determine if a specific mesh or shape is located within or outside a viewing volume, it is far more simple to calculate the bounding volume for that specific shape and then perform a comparison between the planes, if it's a bounding box, or between the center and radius, if it's a bounding sphere, of the mesh, and the specific viewing volume that we are considering. So instead of going polygon by polygon of our mesh and check, is this specific polygon inside or outside the viewing volume? We do not do this. What we do is we calculate a bounding volume and we check, is this bounding volume inside or outside the general viewing volume, the viewing frustum? So this is our goal. So the bounding volume is a volume which includes completely all vertices of a specific object. So bounding volume is a technique of visibility determination which operates at mesh level, at object level. You have much coarser, much wider visibility determination techniques which allow you to work not only at the level of the specific object, but allows you in just one operation to cut away entire groups of objects. Such techniques are not based on bounding volumes, or at least not only on bounding volumes, but are mainly based on the concept of partitioning the scene space. That is, subdividing the space into portions, organize these portions in data structures which can be scanned quickly, so typically a tree, and attach to each node of this tree an information which allows you to locate what is the position of that specific portion. Hello. This kind of strategy is called space partitioning. And basically there are two mainstream methods for partitioning a 3D space, which are namely the octree. The octree imagines that each space can be considered as a cube. When you are considering the root cube, that is the cube which encloses all your space, then you can imagine that you can subdivide the root cube in 8 smaller cubes. Okay? 4 in front and 4 in the back. But then each one of these 8 cubes, which are the result of subdivision of the root cube at level 1, you can recursively subdivide in another 8 cubes at level 2, and so on. So you can imagine that there's a tree going on, and on each node you can store, well, the label identifying this cube. And then it is very easy to start applying visibility determination, not at object level, but at octant level. An octant is 1/8 of the cube subdivision. So if you are already culling out objects at the first recursion level of the subdivision, then you are already cutting away 1/8 of the whole space, and you're not working anymore object by object. So this is even faster. Of course, less precise, less accurate, but faster. We will have, this is just an introduction. I have a few pictures to show you visually how it works, and then it will be very clear, I guess. And there is another strategy which more or less follows the same principle, except for the base criterion for subdivision, which is not in octants, but is in binary spaces. So you just draw a plane crossing the space. This plane divides in a half, the positive half and the negative half, the space. So you go on recursively subdividing the space 2 by 2, and that is why this strategy is called binary space partitioning. So you have basically a tree which just have 2 branches for each subdivision node. The positive branch corresponding to the positive area of the plane, and the negative branch corresponding to the negative area of the plane. So you can understand that working in this way, you can cut away big chunks of your space without even going down at object or mesh level. Okay, so this is what we will see in the first half of the lecture today. So let's start with it. First of all, what we want to do is, since we are going to completely replace a polygon by polygon check with a bounding volume check, the best thing we can do is to be sure that we choose an optimal bounding volume. What do I mean by optimal bounding volume? Well, consider this picture in 2D. These are supposed to be vertices. The first idea you might have, which is very comfortable, is to draw a bounding box around the vertices using planes which are parallel to the axis which I'm currently using to express the coordinates of the vertices. Why do I do this? Because it's very handy, it's easy to calculate, and it's easy to handle, basically. However, not always this is the optimal choice. Namely, in this case, you can see that this bounding box, true, encloses all the vertices of the mesh, but it leaves, well, it encloses also a big portion of empty space. So, if I were checking a collision against something else, I would detect a collision over here, for example, even if there is no actual collision to any of the vertices of the mesh, because the vertices of the mesh actually happen to be much more inside the box, which is around here. So I have a high chance of a false positive when I'm going to collision check or visibility check using such a bounding box. So much better is to find out what would be the optimal bounding box, the one which still encloses all the vertices in the mesh, but leaving as less as possible empty space around the mesh. Not always. This implies, if you are thinking about a bounding box, recognizing what is the natural axis of your mesh. What is the natural axis? Is the main axis along which the distribution of your vertices show a preferential distribution. So you can easily see that in this specific case, where's my pointer here? In this specific case, I can, with my naked eye, see that there is a preferential distribution direction of my vertices, which is more or less this one. So, the rule is, determine which is the natural axis of the vertex mesh. Choose that axis as the first one in the vector space, well, in the frame, we should say, in the frame which is going to be the base for the three axes of the box. The other two come along, because as long as I calculate this axe, I can just take a triplet by creating an orthogonal, orthonormal set of vectors. So, I have one, I use this one and search for another two which form an orthonormal base. Like, for example, this one, and, well, imagine that this is drawn in a way that is supposed to be orthonormal, right? So this is why, last time we met, I was breaking your balls with orthonormals, orthogonal, and check that they are linear independent, etc., etc., etc. Why? We were going to need those things, because this one is one of the examples. Because I can find one axis, but then I need to form an orthonormal triplet in order to stitch together the planes and the equations of the planes which I need to form the optimal bounding box for visibility checking. So this is what we are going to do. Of course, calculating the optimal bounding box is one thing. Another thing is choosing the best shape for your bounding volume. In literature, you can find basically three shapes used for user bounding volumes. These are the box, the sphere, and the cylinder. I have to confess that personally I never used the cylinder in my life, but I have seen papers which were proposing cylinders. They could come in handy in some cases. What I would suggest in implementing an engine is to go using the sphere first and the box second. Why? Because the sphere is simpler to calculate and quicker to check. But as you can understand, it's difficult to have a sphere which is an optimal bounding volume unless you have an homogeneous distribution of all vertices scattering around homogeneously in all directions. Can you imagine that? Just because it's a sphere. So in this case, if I were using a sphere, then the bounding sphere would be something like this, and you can see very well that this is far from optimal as a bounding volume. In order for this to be an optimal bounding volume, I have to find myself with meshes which have an homogeneous distribution of vertices scattering homogeneously all around. So there is actually no preferential, well, no natural axis for the vertex. So there the sphere works well. However, you could think of a two-step strategy. even if you know that the sphere is not actually the optimal shape for your specific application, what you could do is very quickly calculate the sphere on the first step and do all your checking with the bounded sphere. If your checking is negative, already using a bounded sphere, so for example your viewing frustum is over here, so that represents your frustum, meaning that there is a center of projection over here, COP, and your visibility is inside over here because here you have front clipping plane over here and a back clipping plane over here. So everything that will be inside this area will be visible. Everything that will be outside this area will be called out because it is not viewable from the current position of the COP. So this is the mesh. Imagine that it's the enemy spaceship which is moving in your video game or whatever. And you have to determine, do I have to shade and transform and process all the vertices of the spaceship? At the moment, no, because all the vertices composing the spaceship are outside the viewing volume. Whoops, I messed up with my viewing volume. That's okay, never mind. You can easily see that here, even if you're using the bounding sphere, you have a negative result in the test, which is the mesh inside the viewing volume? No. My test is the bounding sphere inside the viewing volume? No. So it's okay. I can call out everything which is inside the sphere. If even the sphere is negative, there is no sense in performing the check again using the box. You see? Because you are sure already the sphere is not giving any result, the box as well will not give any specific result. So you save time because you just calculate the sphere, which is just one operation. You do the check is negative, okay. But imagine that, well, the spaceship is moving, something like this, and then the sphere, if you keep using the bounding sphere, at a certain point the sphere is over here, but your vertices are here, you see? So you have a case in which actually you do not pass the bounding sphere test because the bounding sphere gets inside the viewing volume, but actually the mesh itself is not inside the viewing volume. So you have a positive result of this check, which means, since you know that the sphere bounding volume is not accurate enough, you could switch to a optimal bounding box, and reperform the check again. This time, the check on the bounding box tells that you have no visibility, so it's negative. With the sphere was positive over here, with the box is negative over here. So you know that even if the sphere gave you a false positive, you have no visibility at the moment. So you see, you could use instead. That is why it's important not only to understand how to calculate a bounding box, but also how to choose, that you can choose between different shapes to obtain different degrees of precision. Of course, it depends on what you're doing. Are you doing a video game, so where precision is not, very important? You choose. If you're doing something in which precision is of paramount importance, for example, in medical imaging, then of course you should be as precise as possible, and then you should invent as many techniques to be performant but accurate in the same time. Okay, so I've told you that the first step for finding out how to calculate all the planes, the 6 planes that you need to create the box, you will have to build the 6 planes to form the box around the main direction, which is the main direction of distribution of the vertices composing your mesh. How? Okay, here it was easy. I've seen it, I have drawn it. For me it's easy because I'm using my eye. But how can I find out a method which I can put into an algorithm in my program? So is there a mathematical method which can tell me what are the coordinates of this natural axis? We use a technique which belongs actually to statistical data analysis, in which you can measure the degree of correlation between data components. This has to do with the distribution of probability in statistics, but we can borrow the idea and use the same idea to express the degree of correlation between the coordinates of each vertex in the mesh. If we see that there is a high degree of correlation over one or two specific coordinates of all the vertices in the mesh, it means that there is a preferential direction along which the vertices are distributed. So, for example, if my technique shows me that there is a high level of correlation between the x variable and the y variable in the population, which actually is made up of the vertices of the mesh, and that this correlation, for example, is x more or less equal to y, it means that the main distribution of my vertices is along the bisector x equals to y of my space. This is just roughly. Of course, the matrix, which is called the correlation matrix, is far more precise and gives you the balance between x over y, x over z, y over x, y over z, z over x, and z over y. So you can really have a grasp of the distribution of the vertices in space. So just to give you, introduce you to the tool, this is the general expression of this matrix, expressing the correlation between coordinates, which is called the covariance matrix. It's this baby over here. Shucks. I need this over here. In order to use this covariance matrix, you first have to calculate the average position. The average position is the coordinates of a point which is exactly in the average coordinates of the mesh. Well, it's a virtual point. Probably it doesn't exist in your mesh. It's just the point exactly in the average of all the coordinates of your mesh. How do you calculate this? Given n, the cardinality of the points, so how many vertices you have in your mesh, and p with I, each one of the points, p with I has coordinate x with I, y with I, and z with I, you calculate the average position like this. You sum together all the coordinates of all the points, which are the vertices of your mesh, and divide all the coordinates by the numerosity of the vertices. So if you have 3 points, you sum together the 3 points and divide the vector that you have obtained by 3. That is the coordinates of your average point. Once you have the average point, you are ready to write the covariance matrix. This is the vector form. To give you an idea, this, as you can imagine, is a symmetrical matrix. Because the relationship between x and y and the relationship between y and x in the specific application of a 3D space is symmetrical. This is not so in statistics. You could have that x given y has a certain probability and y given x has a certain other, because probability is about, I don't know, virus spreading or whatever. But in this specific case, we're modeling points, so it happens that the covariance matrix is symmetrical. So, for example, element 1, 2 is equal to element 2, 1, which is x against y, and it is like this. Well, actually, 1, 2 would be x minus m, y minus m, and 2, 1 would be y minus m multiplied by x minus m. But since, okay, right. When you have calculated all the elements of the covariance matrix, you diagonalize the covariance matrix. What does it mean, you diagonalize? You find a matrix which, multiplied in this way by the covariance matrix, gives you a diagonal matrix. That is a matrix which is populated only on its diagonal. Why we diagonalize it? Because in this way, we get rid of the disturbance elements which are at the corners, and we find, well, the matrix which allows me to diagonalize transforms the relationship to something which has zeros in the corner. So it actually gives you, well, shifts the coordinates in a way that you find the space in which there are no deviations according to the main direction. It also happens that there is a rule that tells you how can you build a matrix which diagonalizes another matrix. The diagonalization matrix can be built by using the eigenvectors of the matrix you want to diagonalize. So the reasoning is this. I've built a matrix. If this matrix would represent a set of points which are distributed homogeneously along all the space, this matrix would be diagonal. So, a diagonal covariance matrix expresses the fact that there is no deviation in respect to the main axis. 1, 1, 1 and 0, 0, 0, 0, 0, 0 in the corners. It means there is no deviation. Everything is homogeneously distributed. We want to find a set of axes for which this is true, because this allows us to create the optimal bounding box if we would use this axis. If we are using axes with which the coordinates exhibit deviations in the covariance matrix, then it means that we are not using the optimal axis. This is why we build the covariance matrix with the axes we have, and when we find out which is the triplet of eigenvectors, which can transform this matrix into a diagonal matrix. Why? Because a diagonal matrix is representing a situation in which all points are homogeneously distributed according to the axis. And thus, you find out why we needed to brush up eigenvalues and eigenvectors, because now you have the matrix C, covariance matrix. I want to find its eigenvectors, so I need to know what eigenvectors are, but I do know it. Then I use this eigenvector to form a matrix A. If I multiply this matrix by C and again by A transposed, I diagonalize it to prove that using those axes for transformation, I create a new system of coordinates in which those vertices can be considered homogeneously distributed. Therefore, those axes are the optimal natural axes for that mesh. If I call x, y, z the axis in which I normally express my coordinates, I will call R, S, and T the natural axis of the mesh. R will be the main natural axis, the one which is really the starting point of your reasoning. So this one, R. S and T will be the other two that will follow after that you have calculated R. Okay, this is the general theory. Let's see how the calculation can be done with this example. You see, pencil. So this is a very simple mesh actually, made up of 4 points, P1, P2, P3, P4. What I ask you in this specific exercise is find out what are the vectors R, S, and T, representing the optimal, the natural axis for this specific mesh. Which are the steps? The first step, you calculate the average position. The second step, you use the average position to qualify the covariance matrix. This covariance matrix will not be diagonal. It means that you need to find out the natural axis. To do this, you need to calculate the eigenvectors of the covariance matrix. So you write the characteristical polynomial, because this is what you know, what you need to find the eigenvalues. Once you have the eigenvalues in your hand, which you can do by solving the characteristical polynomial, for each one of the eigenvalues, you calculate the eigenvectors. These eigenvectors are the axes R, S, and T. Namely, the eigenvector which is, the eigenvalue which is greater than the other is the eigenvalue which gives as a result the eigenvector R. S is the second less eigenvalue and T is the third less eigenvalue. Let's see how it is done. Let's do it together. Video lab. Right. Okay. This is the general form of the covariance matrix. The covariance matrix asks me to know the average point and each one of the coordinates of the vertex. If I want to write this in its scalar form, then it would be like this. That at the corners, I have just a correlation with the x coordinate against itself. Sorry, no, it's not the corners, but the diagonal, of course. So on the second element, I will have for y, and on the second element, I will have it for z. This is why, you see, if I have a diagonal covariance matrix with the other elements which are at the corners, so these are on the diagonal, right? C11, C22, C33. At the corners of this symmetrical matrix, I have the relationship between x and y, for example, right? So if there is no deviation in the way x deviates from the median point and in the way y deviates from the median point, so this one is 0, it means that there is completely a homogeneous distribution across the median point between x and y. Do you see? So now you have to check the same thing between x and z. And the same thing between z and y, I guess. Right. So this is how it should be if I were to write in scalar form what I have written in vector form. Let's try and calculate what is this covariance matrix if I have a mesh like this. Do you remember that we have a rule that all points have to be written like a vertical vector? And in order to remember that, if for some reason, for example, graphical reason, I don't do that, I put a transpose to remember that I'm thinking them as vertical vectors. So this is the mesh, well, a small mesh. From this, it is easy to calculate the fact that your median point is actually 1/4 of the sum from 1 to 4 of all these points, which turns out to be 1, -1, and 2. So this is the median point. Now, if you plug in the median point over each one of these, you build the covariance matrix. Let's do it. Come on and do it. Come on and do it. So it's the same thing. 1/4, then you have x, y. For each over, you have to sum. That is, x1, it will be -1, -1, so it will be 0.
Then you have to do the second one. It would be 2 minus 1, it will be 1. So you already have 1 plus, etc., etc., etc. You sum all the 4 xi, x1 minus mx to the square, x2 minus mx to the square, x3 minus mx to the square, x4 minus mx to the square, sum everything together and divide by 4. If you do this for all the others, then you have that your covariance matrix has this form. It would be 3 over 2, 1 over 2, 3 over 4, 1 over 2, 1 over 2, 1 over 4, 3 over 4, 1 over 4, and 1 over 2. Okay, this is your covariance matrix. Is it diagonal? No, it's not diagonal, because you have values in the corners over here. These values in the corners over here tell you that you do not have homogeneous distribution, x related to y, y related to z, z related to x, because there are values. You have deviation, unbalancement around the median point. So your bounding box will have empty spaces in some directions. What would be the axis along which the planes of your bounding box would allow you to have a diagonal covariance matrix? That would be nice, because a diagonal covariance matrix would tell you that all the points are distributed like in a mirror around the axis. And this is a guarantee that a box built around those axes is an optimal bounding box. So, to find out what are these axes are the eigenvectors of this diagonal matrix. So we find out first what are the eigenvalues. How do I do it? This by creating the polynomial characteristic. The polynomial characteristic is the determinant of the matrix itself minus the eigenvalue that I'm looking for and the identity matrix. If you do this, it means that you have to find the determinant of this matrix. The determinant of this matrix is the polynomial characteristic. Being a 3 by 3, the polynomial characteristic will be of the third degree. How many roots it will have? At least 3. Okay. If you find the roots of the polynomial characteristics, you will find that the first eigenvalue, which is the one with the bigger value, is this. The second eigenvalue is this one. The third eigenvalue is this one. This will allow you to find the first eigenvector, which will be r. This will allow you to find the second eigenvector, which will be s. This will allow you to find the third eigenvector, which will be t. R, S, and T will be an orthonormal triplet, because there are 3 eigenvectors of a symmetrical matrix, which you will use to form your bounding box. Like this. Now you have to solve this equation by plugging in the first time the first one, the first time the second one, the first time the third one. And you find out the eigenvectors. It turns out that the eigenvectors are like this. Of course, you don't have to make all these calculations by hand. I mean, usually you write a program or an algorithm and you use libraries that allow you to do this, okay? But I'm just showing you the numerical example in order for you to understand the steps that your software will have to follow. So these are the results, okay? Or if you don't like these numbers, you can somehow factorize them or normalize them. But these are basically the 3 axes, orthogonal axes, that you will use to find the planes. Right, but now, I have this axis. These are just the axes. I mean that I have found the orthonormal space, but along which my vertices are homogeneously distributed. Okay? But now I want to know which are the planes of the bounding box, because these are just axes. They are not a box. Now I have to build the box. To build the box, I need the 6 equations. The 6 equations of the 6 planes which make up the box. Let me make a bigger drawing. So, if this is supposed to be R, S, and T, it means that you have a privileged direction along R, and you have a symmetry, you see, along R, along S, and along T. Why? Because you will be your covariance matrix will be diagonal according to R, S, and T, which will never be according to X, Y, Z, which it was the direction that we will be coming for. See? If you consider that we were coming from X, Y, Z, in X, Y, Z you have no symmetry. Your covariance matrix was not diagonal. But now that you're considering R, S, and T, you are looking at your vertices in a way that they are symmetric along the whole axis. You see? That's why your covariance matrix is diagonal. And that's why you have an optimal bounding box. You can figure it out what it is, because you can see that one will be over here, one will be over here, one over here, one over here. So it will be something like this. So can you imagine the plane which is actually intersecting the axis over here, and it's made something like this, somewhere like this, and you have another plane like this. Okay? And then of course you would have another plane like this. And another one like this. You see what I mean? And then of course you need the other two in front of them and on the back. But I'm not very skilled in drawing, so imagine that you can put in front and in the back. So you have 6 planes. these six planes are stitched together and form your box, right? Good, but still we don't know how to calculate them. Right now we have visualized them. So actually it has to do, you see, let's just pick in calculating the two side planes along the main axis, which is R. It works like this. That, well, the general formula is this one, that the two parts over here is R, and the negative of the minimum of the scalar of pi and R. This is, well, sorry, this is the recipe for this one. And for this one, this, of course, is flipped. Do you remember that I write, this is an equation of a plane, and using this form, you remember that the general equation in vectorial form of a plane can be written as this, right? You remember that day in September? Being n, the normal, marking the positive side outgoing from the plane, and d, that's the fourth element of the Cartesian equation, right? So it's the same thing here. I'm not using the normal, but I'm using r, meaning that actually, you see, r is marking the positive direction outgoing from this plane. This is r, you see? It's positive along r. Then, remember always, in viewing volumes and in volumes in computer graphics, every time, always, when we're dealing about planes, in viewing frustum, in bounding boxes, all the normals are oriented in the inside, right? Like this. So, the equation of this plane, you see, is actually has an outgoing normal which is flipped in relation to r, right? So it's minus r, and the maximum between all the scalar products you might want to make between pi and r. That's the one to get it. So if you have this, then you have everything. You have the planes. These are the two planes, because r, you have it already. It's over here. A, B, and C. And D is a scalar. What is the result of this operation here? It's a scalar, right? Because that's a scalar product. That's why it's called a scalar product, because it gives you a scalar. Duh. But you have to get the minimum and flip its sign. If you do this, then you will find your plane, completely determined by the first three elements of the axis and the fourth coordinate over here. Let's make a numerical example. Actually, these numbers are very difficult to handle by hand, so I'm actually changing a little bit. Imagine that we have an R. Just to be very simple, so you understand it. It's a very specific case in which R is Z over here. Okay? So it's like x, y, z. So the general equation of R, well, the vector form of R will be 0, 0, 1. Right? This will be R. Just its direction. And for example, I know already that why do I need to take here the maximum of the scalar product? Look, because the scalar product between a point, imagine that this is P14, okay? The scalar product between P14 and R is this over here, right? This part over here. So, if you imagine that the farthest away along R is this one, P66, okay, then the scalar product between P66 and R would be this quantity, right? Which is exactly the position of your plane. You see it? Because you don't see it very well in the monitor over here. But, I mean, is the picture getting a little bit grainy, but... So, this is why here you have to pick the maximum value between Pi and R. So if you imagine that this P66 is actually 0, 1, 5. Then you have that P66 scalar R is 0, 1, 5 scalar by 0, 0, 1, and you have it as 5. So it means that the equation of the plane that you're looking for is 0, 0, minus 1, 5. This is the plane. I'm sorry. Okay. This is actually, well, if you would want to take in coordinates, this is A, B, C, and D, right? So it would be minus Z equals to 5. I'm sorry, minus Z plus 5 equals 0. Okay? Because it's X plus BY plus CZ plus D equals to 0, right? So minus Z plus 5 equals to 0, which is Z equals to 5, which is this plane. Okay? Does it? This is why I chose very simple numbers, because otherwise you don't understand. But once you put your trust in the method, then you can just forget everything else and just apply the formulas and what the fuck you do. Okay? Over here, while it's minus minimum, because you are flipping in the other direction of the axis. So, here it is R because your plane has the positive side over here. But when you're making the scalars are working only in the negative region. You see? So you have to reason as the minimum. Why the minimum? Because it's the smallest quantity in the minimum that is over here. Right? So, minus 1 over here will be not good. You need here minus 8, for example. So you need the minimum. But then you have to flip it with the minus sign. Why? Because of this. Imagine that this is point 92. And its coordinates are P92, 0, 1, minus 8. Then we play the same game, right? P92 scalar R is 0, 1, minus 8, 0, 1, minus 8, 0, 0, 1. It gives you minus 8, which is exactly this quantity over here, because I'm making the scalar of this point, which is the farthest away on the other right, against R. So this quantity over here is minus 8. So my equation becomes R minus minimum, which is minus 8. So minus 8, 8. Okay. Does it work? Well, it worked because this actually means 0, 0, 1, which is R, 8. Sorry. Because I see it, so for me it's natural that you see it. But, okay, because it's outside the clipping window, you see. and I have no algorithm at the moment. I'm implementing it, so it's not working right now, the clipping. So 0018, so that will be z plus 8 equals to 0, right? And that would mean z equals to minus 8, which is exactly this one. Z equals, so it works. So it works. Okay, so what is the ending story? The ending story is that you have to get this, then you have to make all the scalar product against R and mark which is the maximum and which is the minimum. Flag those two and use them as the fourth element to build the planes. Then now you are set on the R axis. Now you have to do the same thing with the S and the T axis. What are the formulas for the R and the T axis? Well, they are the same actually. So I think I have them over here. PC. So this is the general way to go. Once you have R, S, and T, you start making all the scalar products. You mark the maximum and the minimum. And these are the 6 planes of your bounding box. This is the optimal bounding box, and these are the 6 planes. Now, since you have planes here, and you will have planes in the viewing frustum, you will be able to check if points belonging to each one of these planes are inside or outside, using what? A scalar product between the coordinate of the point and the plane. Do you remember? L scalar Q equals to 0 means the point Q is on the plane L. If L scalar Q is greater than 0, means that Q is on the positive side of L. If L scalar Q is lesser than 0, then it means that Q is on the negative side of P. Negative side of P, of L, negative side of L, it means outside the volume. Why? Because all my planes are pointing towards the inside. So once you know the planes, once you know a point, you can easily check if a point is inside the volume by just taking the equation of one of the planes, for example this one over here, scalar product it, like this. So if this is L, and this is P, you make L scalar P. If this equals to 0, it means that P is exactly on the plane. If P is greater than 0, it means that it is inside. If it is negative, it means that it is outside. Because the positive side, by convention, by construction, is always pointing toward the inside of the volume. Right? So, do you see how it is easy to check this thing? No, really, it could be worse. Okay. Okay, now you know the planes. Now you would like to know the size of the sides. How long is the side of the box? Well, you can make your calculation. For example, we knew that one was 5, the other one was minus 8, so you make the difference, okay? 5 minus minus 8, and you have 13, which is the side of your box along R, right? So this is the general equation of this way of reasoning. Now you have A, B, and C, which are the sides, the length of the 3 sides. And why are you interested in such a thing? Because knowing A, B, and C, you can find the center of the box, which is Q. It turns out that if A is defined like this, B is defined like this, and C defined like that, then the coordinate of the center Q is over here. AR, BS, and CT. This is the position of Q, but mind you that the coordinate I, A, B, C are expressed not over X, Y, Z, but are expressed over R as T. Okay? Right. Oh, yeah, I had it here. Oh, well, that's okay. It's more entertaining if we do it together. Okay, but if you didn't understand anything and you couldn't take notes, I don't know why, you have it here. So you didn't lose anything. And actually, this exercise with numbers and etc., you have a scanned copy of what I wrote, I don't know, several years ago. I scanned it and I put it on the web. So if you didn't manage to copy it, you have it on the web page of the course. Mind you, there is also the pencil here, which means there might be an exercise in the exam which asks you something about this. Okay, so be careful that you have understood how I got to the final result. That's it for the bounding boxes. That was cool. We also need to know how to build bounding spheres. And I told you already why an example of why we could need both bounding spheres and bounding volumes. How do you start building the bounding sphere? Imagine that you have a set of points making up your mesh. So vertices P1, from P1 over to Pn. You determine which is the main natural axis R, as we have seen already. Along this main natural axis R, you select which are the points Pk and Pl which are on the minimum and maximum extension in relation to that direction. How you do that? Like we did already. We make the scalar products and we pick the minimum scalar product and the maximum scalar product. So it's the same thing. What we're going to do here is we have several points. This is supposed to be XYZ. XYZ do not help me. I find R, which is the natural axis direction. Over R, I start finding the minimum scalar product, so P1 and P99. This is mean PR, and this is max PR. So these will be my maximum extension and my minimum extension from my sphere. Then, obviously, what I do, I go and look for the center. So this will be Pk and Pl. Pk and Pl divided by 2. So what do? I take this plus this divided by 2. This will be Q. This will be the center of my sphere. Then I just need the radius. the radius will be the norm of, you choose pk or pl, let's say for example pk minus q, so this quantity over here, right? So I have the center, I have the radius, I build the sphere. This will be my bounding sphere. Oh, it's a bounding egg, I'm sorry. It's okay. There's something missing over here. Do you see what it is? With this, in this way, okay, I have a nice bounding sphere, but I'm sure that it bounds optimally the vertices along the r axis. But who guarantees me that everything is correct along the s and along the t axis? I think I could have, I don't know, a point here. You see? Can you reason it in 3D? So if my sphere is doing like this, it's okay along the r axis, but not along this one point. This is because, well, choosing the main distribution direction tells you that most of the points are around r. But it could escape that one point is not around, it's around r, but has a different distribution around s or t, for example. Hello. I have a déjà vu. You're not a student anymore in this course. No, okay, that's fine. That's why you have a thesis in your hand, I guess. I'm just kidding. Okay, so actually what we have to do is we build a sphere, but if we want it to be precise enough, we would have to check the sphere that we have built and see if I have any points outside the sphere. I have it in the slides. So the sphere is a good approximation, but it does not guarantee to contain all points. Therefore, if I wanted to be precise, I would have to inspect each point and test whether it lays inside or outside the sphere. So I have to check for every p if the difference between its position at the center to the square is greater than the square of the radius. If it is, it means that that point is an outlier. If I find an outlier, then I could use this outlier as a pivot point to enlarge the sphere. How do I do it? Imagine that this is the outlier. This is the sphere I got at the first step. Then I found out an outlier over here. What I have to do is to keep fixed one of the extremes. Let's imagine that it is G. Compute the new direction between the outlier and G. So I draw the line between the center, the outlier, and G. Recompute the new center and the new radius, and draw the new sphere. Now I have to check if there is still an outlier even with this new sphere. And so on until I've checked all points and I don't find outliers anymore. Okay, so it's not the best method, but it's simple enough also to implement. At the end of this recursive procedure, you have the best fitting bounding sphere for the mesh, which is not actually the best bounding volume for the mesh, right? We have said that already. But it has the advantage, the benefit that it's quick to calculate, quicker than the bonds. Okay, I think we can take a small break,
before facing the last step, which is spatial partitioning, of which I will just say you a couple of words, and then we will start my favorite part of the course, which is colors and light. Okay, see you in 600 seconds. Okay, welcome back. Those of you who haven't dozed off in the meantime. Let's cover in a few words now that we know bounding boxes, we can just finish off the topic of visibility determination by introducing the equations of the Frustum planes. These are the other equations of the Frustum planes that you can use to compare with the planes of your bounding box to check for visibility. This is the Frustum. The parameters that are used to define the Frustum are represented in the picture. Namely, you have the focal length E, the aspect ratio A. The aspect ratio A is the ratio between X and Y. And the near plane distance, which is N over here, and the far plane distance over here. So given these definitions, the equation of the planes for the Frustum are the following. They are in the vectorial form of the planes that we came to know by heart right now, so ND. For the near plane, you have 0, 0, minus 1, minus N. For the far plane, 0, 0, 1, F. And then for left, right, bottom, and top, it's a little bit more complicated because they are not parallel to the plane, but they form a pyramid. So it depends on the aspect ratio and on the focal length of the viewing volume. So we are not going to explain why exactly these are the results. These are the results. They can be useful. You don't have to know them by heart, actually, except the near plane and the far plane, because they're so easy. So you can actually work them out if you need them by reasoning. This, of course, is a little bit more difficult to work out. If by chance there will be an exercise asking you to check over a Frustum plane, if the plane is not near or far, it means that I had a bad day when I wrote the exam. But in any case, I promise that I will give you the equation of the plane. You need to check if it is not near or far. If it is near or far, you need to know, because it's easy, and actually you can work out it with reasoning. Speaking on this, did I mention that the exam is a closed book exam? The exam is a closed book exam. And somebody asked me during the break what it has to do for the project for this exam. And the answer is nothing. There is no project for this exam. For this exam, there is just a written exam. You come the day of the exam, you answer to the questions, and if you are good enough, you finish the exam. That's it. No project. If you like the subject, you have the possibility to put in your plan laboratory of computer graphics, which is in the second semester. That, yes. You don't have to attend anything because there's nobody in the laboratory. It's just a placeholder for 80-90 hours of your work in a group for making a project about computer graphics, which I pay 2 credits and a half. That's it. But it's in the second semester. For this exam, so computer graphics, first semester, you just come with pen, pencil, and a pocket calculator, do the written exam, and that's finished. Okay? And it's closed book. So no notes, no books, no calling your mother to ask her the equation of the right plane of the viewing Frustum. Okay. Good. We know the plane. We know bounding volumes. We know the equation of the Frustum. What you don't know is exactly how to make this check.
So I know how to calculate the planes of the bounding box, or how to get the bounding sphere. I know the equation of the planes of the viewing frustum. Good. Now my goal is to check whether any part of the mesh which is inside the bounding volume, which I know, is by chance inside or it is outside the viewing frustum, whose planes also I know now with the equations. Good. How do I make it? How do I do it? I do it like this. So testing against the viewing frustum using a bounding volume. First method, test using a bounding sphere. So my mesh is inside a bounding sphere. I want to test it against the viewing frustum. You create a bounding volume that is the bounding sphere. We reduce the problem to testing the intersection of a point of the bounding volume against a modified frustum. That is, the idea is, I take the frustum, which is this one, and I enlarge the frustum of a quantity which is equal to the radius of the bounding sphere. Why? Because if I do this, then I know one special point which I can check with a single scalar product for if the point is belonging or not to the plane of the viewing frustum. Which is this point? Any of you brilliant guys? Which point? You have a bounding sphere. I tell you, we want to reduce the problem checking if one point of the bounding volume belongs to the plane of the viewing frustum. Which point of the bounding sphere would you choose? What? I would choose the center of the sphere. Because the center, you know. The sphere, imagine choosing a point on the bounding sphere. That gets tricky. How can you know which is the best point to choose? Well, you know if you can see the sphere, but since you are programming this, it's very difficult to devise an algorithm to choose a point on the surface of the sphere. So the smart thing is, I choose one point that I know very well, which is the center of the sphere. However, if my goal is to understand when the sphere touches one of the planes of the viewing volume, I cannot do this with the center. Why? Because the center is inside the sphere. So what do? I'm not checking if the sphere is touching the walls, so to speak, of the viewing volume. I'm checking if the center is touching the shifted walls of the viewing volumes. Do you see? I enlarge the viewing frustum of exactly the same quantity of the radius. At this point, I check against the enlarged frustum if the center of the sphere belongs or not to one of the planes of the enlarged frustum. As soon as the scalar product between the center of the sphere and the enlarged plane of the frustum against which I am checking is equal to 0, that means that the sphere is checking the actual, is touching the actual frustum. Do you see? Do I need to draw this? Look. Do you know one of the basic rules of engineering? One of the basic rules of engineering is KISS. You know what does it mean? Keep it simple, stupid. And the last S is most meaningful. So, why do I have to break my head in choosing a point on the surface on a sphere? For in this situation,
I have a plane, I have a sphere, I want to check when the sphere is touching the plane. I know for sure this point, so I'm actually, this plane is L, I'm actually getting another plane, which is L minus R, when the sphere is moving, moves, at a certain point, this is Q, when L scalar Q equals to 0, it means, I'm sorry, L first. When L first scalar Q equals to 0, it means that Q is exactly on that plane. But the distance between these planes is R, and the radius of the sphere is R. Then it means that the sphere is touching L. You see? So what you have to do is taking the plane, shift it up of a given quantity, and then check the shifted plane against the center of the sphere. If it is not 0, you use the sign of the scalar product to determine if you're already inside or if you're still outside. Okay? That's cool. That's cool. So basically, you can check if the shifted plane scalar, the center of the sphere, is 0, or if you're still considering the plane before shifting, then you have plane before shifting scalar Q is less or equals minus R. If this holds, then the sphere does not intersect the frustum, and the mesh inside has to be cut, the mesh inside the sphere. Otherwise, a part of the sphere is inside the frustum, and the object has to be kept. Unless you want to do clipping. Then you have to decide which part of the mesh to clip, which is a completely different story. This is in general okay, but we have some soft spots. May I close it? We have some soft spots, by which I mean there are some situations, we have some situations in which the sphere happens to be inside the plane of the frustum, but it's actually not inside the viewing volume. Like, for example, here. So this is a false positive. With the tools that we have, right now there is actually no way to easily check this, except going for a finer volume. For a finer volume which is not a sphere. Okay, so this is how to check the sphere, very easy. We shift the plane, we check with a scalar if the center belongs to the plane. If not, we check the sign. By the sign, we understand if it is inside or outside. Good. Now with the box. How do we do with the box? Because the box has not a radius. And it depends if it is a box, no, like this. It depends the way you turn the box. Okay? So it's a little bit more complicated. So, to do this, well, we start saying it would be nice if we could use the same approach of the sphere. But the problem is that the box doesn't have a radius. So we invent a definition which defines the radius of a box. What is the radius of a box? The radius of a box is called its effective radius. And the trick is, I use the definition of effective radius to calculate the radius of the box. Then I use this radius to apply the same trick as I did with the sphere, only that it is a box.
it works. The only thing that you have to keep in mind is that in a sphere, it doesn't matter how the sphere is positioned according to the plane against which you're making the text. The radius is always the same because it's a sphere. The radius is always the same. In the effective radius of a box, the radius changes every time the mutual position of the box against the plane you are checking changes. Why? Because the definition of effective radius is the following. The effective radius is a half of r scalar n plus s scalar n plus t scalar n. H scalar, it's in its absolute form. So if it comes out negative, you have to choose it positive. Sum everything and put it in a half. That's your effective radius. It's very ingenious. I mean, it's simple yet effective. This is the normal of the plane you are checking. So, actually, what is the definition of effective radius? It is the sum of this segment plus the sum of this segment. So, now, if you shift the plane up of the effective radius, you can do the same trick of checking when the center of the box will be belonging to the shifted plane. Now you understand that as soon as you rotate the box according to this plane, everything changes. Why? Because your corner will be farther away, but also your effective radius will change, because all the scalars will change. They will be shorter, namely. So, the idea of this approach is that you can calculate this, but if your box is moving and spinning, so to speak, you have, at every degree of spinning, you have to take care that your software has to recalculate the instantaneous effective radius according to time to check in that specific time the collision. This is the only snag. But for the rest, it's the same thing. You get the effective radius, you check the scalar. If the plane of the frustum, scalar, the center of the box, is less or equal than minus the effective radius at the given time, then you don't have collision. The box is not visible. Okay? That's good. This is, of course, a bidimensional example, but you can easily think in 3 dimensions. Just think this one as a box. You just need to add the third axis. Okay, so this is how you make your visibility test. Be it a sphere, be it a box, it doesn't matter actually. Well, it matters, but we pretend that it doesn't. We take the radius, we shift the plane, we make a scalar product to check if the center of the bounding volume belongs to the shifted plane. This is our test. Okay. This kind of visibility determination test can be done at object level, at mesh level. For every mesh belonging to the scene, you calculate the bounding volume and you make the visibility test. This could be burdensome. I mean, it could take a lot of work if there were many objects in the scene. If you just have 2 objects in the scene, that's okay. You calculate the bounding volumes. You do everything with the bounding volume. But if you have many objects to take care of, then probably this idea of following the bounding volume for each one of the objects in the scene may not guarantee you performance. The first thing you might have to do in that case is to first cull away as much as object is possible, and then focus only on the surviving objects. This is exactly the goal of the spatial partitioning technique. As I told you, there are 2 basic techniques when we apply spatial partitioning. One is using subdividing space in octants, which forms a data structure which is called an octree. or subdividing space 2 by 2, which is called binary space partitioning. This is the concept of octree. Octree is in 3 dimensions. Quad tree is in 2 dimensions. Here you see a recursive subdivision using the quad tree concept because it's a bidimensional example. But you just add 1 dimension and you have an octree. I have my bidimensional space. I divide it in 4 sectors. Each one of the 4 sectors I divide still in 4 sectors. Each one of the 4 sectors I divide still in another 4 sectors. In this way, I have several sub-areas, sub-sectors, which determine a specific part of the space. The position and the content of each one of these sub-sectors can be organized in a data structure. For example, this one. This is the root structure. This is the quadrants at first level. So this one is this one is this one is this one is this. If I am trying to remember why this one is black and why this one is white. Does it say it here? A quadric by dimension corresponding to the each node in a quadric as most for some. If the nodes are any pattern does not include completely this one object is different. Okay. When this black, it identifies it is not written here, but I remember. It identifies a quadrant which completely coincides with an object. Okay. I will make an interactive drawing together so it will become clearer. But the idea is here. If the quadrant does not have any object inside, or it is completely occupied by an object, it is not subdivided. So this is the first subdivision at the first level. Here you have an object which completely covers the first sector. Then you have the second sector which is completely empty. Then you have the third and fourth sector which contain something, but they are not neither completely full or completely empty. So you need to subdivide again. So you go to second level subdivision. Each one of the subdivision has maximum 4 segments. So over here, this segment is completely empty, this segment is completely empty, this segment is completely full. This is neither completely empty, neither completely full. So I go subdividing again. Okay? So if I'm looking for a specific object, for example, object number 1, I go through the tree and I say object number 1 completely covers sector number 1. Then my problem reduces to, is sector number 1 visible or not visible at the moment? And it's very easy to understand because I have the plane equations of sector number 1. Now I'm looking for object number 32. Now object number 32 is over here. I know already that object 42 is actually under sector number 3, subsector number 4, and subsector number 3. So the problem shifts not to check the specific object, but to check if sector number 3 is visible. If sector number 3 at the first level of subdivision is altogether not visible, then I don't need to check anything. I can call everything, even all the objects that are behind it, below it. You see? So the problem is taken at a higher level. I am checking whether sectors are visible or not, and not objects are visible or not. In this way, I can eliminate entire groups of objects belonging to sectors which are not visible in a very, very quickly, because I'm just checking cubes, octants. When I determine which is the surviving octant, then I can determine which are the objects belonging to the surviving octant and perform visible determination at mesh level, at object level, only for the objects belonging to the surviving octant. Is it clear? Did you understand, or do you need me to make a drawing, an interactive drawing?
Yes, no, maybe. Yes? Well, you have to decide. Here you don't understand. Here you don't understand. It's just a quick drawing. But the idea is there. So you have to decide. This is 1, this is 2, 3, 4, 5, this is 6, 7, 8. It depends on how you want to implement your algorithm. Any other questions? The question was which is the order in this picture for labeling the nodes. You label them as you wish. The important thing is that you label them in a smart way. I mean that your algorithm works. This story over here explains you the visibility test is using the octree, which is something that I already told you, but you have it here in writing. And this is the other possible approach, which is binary space partitioning. With binary space partitioning, the foundational idea, which is dividing the space to determine which objects are belonging to which part of the space, is the same. It just changes the technique I'm using for subdividing the space. Here I'm just taking a root plane, the root splitting plane. This plane is like a wall, divides the space in two. The positive side, the negative side. The positive side is the one according to the outgoing normal of the plane. So now you have a binary tree starting from the root splitting plane that tells me that there are objects belonging to the positive plane according to root, plane A, and objects which are actually laying on the negative side of the root splitting plane A. So I go on splitting. I can split the positive side of A in two parts using plane B. So I will have a part which is the positive side of B in the positive side of A, and so on and so forth. All the nodes can be arranged in a binary tree, and objects can be labeled as belonging to A or B or C or D, etc., etc. When I will be doing the visibility determination, first thing I will do is, am I looking at the positive side of A or at the negative side? If I'm looking at the negative side, I already say that everything which is on the positive side of A can be called away safely. So I focus on the other side, and so on. Okay? That's it. And this explains to you the same story again. And it's finished for visibility determination. Good. What do you have to remember about visibility determination in order to safely pass the exam? Let's see. You have to know spatial partitioning, what it is, how to explain it in your own words. You need to know how you can perform a visibility test against the frustum planes. You have to know more or less how to calculate the optimal bounding volume. What is the procedure when you want a sphere, a bounding sphere, or a bounding box? Then something about hidden surface removal, which is the thing about the Z buffer. What is the Z buffer? Why do we need the Z buffer? Basically, I think it's this. These are your take-home messages. Let's see if I'm missing something. Yes, clipping. You have to know clipping. It could happen, for example, that there is an exercise on Lion-Bursky. This is something when I had a very bad day. So you get to have Lion-Bursky. What is clipping? How does it work? What are the possibilities? That's it. That's really it. Okay. Now, to my favorite part of the course, as I told you, which is... what's happening here? Activate external content. Lighting. and shading. Light, colors, and matter. Yes. We will start from the obvious, but not so obvious actually. Without light, there cannot be color. So, the color you have, we see color only because there is light interacting with matter. What is the everyday evidence of this? That if you turn out light, you don't see colors anymore. You sit in pitch dark and you don't see colors. Even if you open a little bit, I don't know, the door of your dark room, just a tiny fraction, so some lights comes in, then you start seeing things, but still you don't see colors. You see everything grayish, brownish, but you cannot really tell colors. Okay? This is like, for example, I don't know, your girlfriend is trying on a wonderful dress. Okay? What does she do? She goes to somewhere with light in order to see the real color. Okay? Or the usual problem, are these trousers brown or black? Okay? Or blue or black? You don't understand. What do you do to understand? You go to somewhere with a better light. So it's not only the presence or absence of the light, but it is the quantity of light that you have that helps you to determine how the color appears to you. So it was obvious, but maybe not that obvious. What we will do in this part of the course is to show you how we did kiss this thing. By meaning, this is a very, very complex problem. Namely, to solve it, to really solve it, there is in theory something which is called a global illumination equation, which, if we were able to formulate and solve, would tell us in every point of space which is the quantity of light energy, light emission, in every point of space. Unluckily, this equation is so complicated because it is actually 6 variables integral, so it's an integral 6 times, integral, over the x, the y, the z, the theta, the phi, and the lambda, where x, y, z is the position in space, theta and phi is the direction of one single ray emitting from a light source, and lambda is the integral over all the wavelengths which are emitted from that light source. If we were to implement the solution, the analytical solution of the global illumination equation inside our rendering engine, we would have no possibility of calculating in real time shading and colors. So what do we did? We kissed the problem. We found out a very simple way, a very empirical way, which is based on vectors, actually 4 vectors, but that it gives you a nice result, well, not photorealistic, but acceptable in a very quick fashion, very simple fashion. It's a geometrical based approach which has nothing to do with the physics of the problem. It's really something that we invented. Well, we not invented. Mr. Fong invented it. But, well, he invented well, and we're grateful to him. So, we will see what is the Fong model and why we use the Fong model to represent quickly how light interacts with matter in our scene to produce color. So this is our goal, and we start. So I told you about this myth.
which is the global illumination equation. There are actually two sides of the problem. How to describe in general the illumination of the scene. So choose a model. Choose a model for describing easily how the scene is illuminated, how light interacts with material. That is called lighting. A lighting model is an approach to easily describe the interaction between light and matter in a scene. The result of the lighting model is a simple formula or a simple algorithm which tells me in this specific point of space you have so much quantity of light energy. Good. Now what do I do with this quantity of light energy? I have to decide the color. The algorithm with which, given the fact that I know how that specific area is illuminated, from that input I determine the color to give to the pixel. That depends from the shading algorithm. So lighting is this, I decide how to describe the light problem. Shading is, having solved this problem, I calculate the color of a specific point on my mesh. That's the shading. The shader is an algorithm which decides the appearance of a specific pixel or group of pixels on my mesh according to specific parameters. There are two fundamental approaches when I'm dealing with lighting models, with illumination models. The local approach and the global approach. Mind you, this is the, open quotes, save your ass question at the exam. I mean, usually there are desperate situations and this is really the question at which you have to answer and which saves you usually. When I'm desperate, I don't know what to ask, I ask this one. What's the difference between local illumination models and global illumination models? If you don't know even this, you are sacked. Local models. A local model is a model which describes light interaction of just one object or one element at a time in the scene. So it considers the light sources, all the light sources you have, a specific element in your scene, and the interaction between the light sources and that element. Stop. That's local, because the reasoning is local only to that polygon, only to that vertex. It depends the item, the element that you're considering. Whereas, in a global illumination model, it is not sufficient to consider just one single polygon or one single object in the scene, but you also consider how the single element interacts with other surrounding elements in the scene. In the local illumination model, the fact that your computation is local to a specific polygon prevents you from calculating global-wise effects, like for example shadows, like for example if there is another object which is obstructing the light source, which is the reason why shadows occur, transparencies. So if your object is transparent, what is the other object that you see through it? You don't know because you're evaluating the colors locally. To know this, you would have at least to take into consideration that polygon and the other one. Mutual reflections. Now, very soon it's Christmas, so Christmas ball, which are very shiny, and you can see inside the Christmas ball all the other balls and lights. So you can do that because in our brain there is a rendering engine which is working in a global way. But if God put in our head a local rendering model, we wouldn't see no shadows, no reflections, no transparency, no nothing. So, for every effect for which we need to take into consideration mutual interaction between all the objects in the scene, the illumination model has to be of the global type, not of the local type. Of course, local illumination model is much quicker to compute and much easier to implement. Global illumination model, since it requires the knowledge of the whole scene and the whole interaction between objects, at the same time is much more difficult to implement and it requires much more time to compute. But that's the difference. Okay, rendering and radiosity, I think I introduced them already during our first meeting. I wanted to tell you the three basic ways in which light interacts with matter to produce color. It all depends, well, matter, as it is defined in computer graphics, has its own color. So you will be able to assign a color, RGB, to an object, to the matter of the object. But another important thing is that you have to specify the kind of material the object is made of. And specifically, our model considers three possible different kinds of surfaces: specular surfaces, diffuse surfaces, and transparent surfaces. Do you know this already? Did I say already? I don't remember. Sometimes I mix up courses. So, very briefly, specular surface, an ideal specular surface, it's blinking pleasantly. An ideal specular surface is a surface such as all the outcoming light from the light source is reflected by the surface, and this reflection is concentrated in a very narrow angle. Ideally, everything is reflected with the same angle. This is ideally. So, same energy going in, same energy going out. There is no absorption of energy by the matter whatsoever, and there is no scattering. So, it enters with an angle, and everything bounces back with the same angle. This is the ideal situation. Then there is the real situation. In the real situation, you have a certain percentage of absorption of energy from the surface. So some energy comes in, part of this energy is drained by absorption by the material of the surface, but most of the energy goes away anyhow, following an angle which is, sorry, this is my wife. Not a good moment. I put it silence. Sorry. Ideally, I was saying, but in real reality, you have some part of absorption, and the reflection happens in a narrow angle. The narrowest the angle, the most mirror-like appearance the object has. So a mirror has a very narrow reflection angle. Something which is not exactly a mirror, but it's shiny, has an ampler, a wider angle. Diffuse. In diffuse, the ideal diffuse surface has no absorption, so everything which goes in goes out, and the scattering is homogeneously distributed along all directions. This is the ideal. You have scattering, but if you could subdivide the circle of the scattering, every little slice will have the exact same quantity subdivision of energy. So you have
perfectly equally distribution of the scattering. This is the ideal situation. The real situation, in reality, the material on the surface absorbs a part of the energy, and the scattering has privileged direction. So in some areas, you have more energy reflected than in other areas. Then you have transparent surfaces. Transparent surfaces deflect in this way energy, and in ideal situation, there is no absorption. In real situation, you have some kind of absorption, a partial reflection, but most of the time, deflection. So these are the three types of materials. I have been talking about light as energy. Yes, because I'm sure you know that light is an electromagnetic radiation, and as such is an energy carrier. Actually, light has the same nature of radio waves that we use for transmission, X-rays, or gamma rays, which is energy emitted from particles, which are radioactive particles, which are decaying. So it's actually a continuum of energy, of waves. And when, do you know these things? Yes? Yes, okay. So when waves are in a certain range of wavelength, then they get visible, and this is what we call light. Under a certain range, there is an area which is called the infrared, which we cannot see. Over a certain range, there is an area which is called ultraviolet, which as well we cannot see. From which you can understand that red has the less energy, and violet has the most energy carried around. The energy is actually related to the frequency. At higher frequency, the wave is carrying more energy. So these waves over here have very high energy and very high frequency, which means a very small wavelength. And on the other side, you have a very big wavelength, which means a very low frequency and low energy. Right? You knew that, I'm sure. In the visible spectrum, Isaac Newton was the first to determine which are the dominant wavelengths, around which he named the cardinal colors of the visible spectrum. These cardinal colors are 7 and are defined as following. Violet, this is the wavelength. This is the shortest wavelength. Therefore, the highest frequency. Therefore, the highest energy. Indigo, blue, green, yellow, orange, and red. This is what we call, in elementary school, the rainbow colors. The colors of the rainbow. At the university, we call the dominant colors, the dominant wavelengths in the visible spectrum. We lose something during time, and it's a pity. It's better to call them the rainbow colors. Okay, good. This is very roughly the theory, well, the physical aspect of this. We subdivide, well, we will see this much better during the second semester when we will be talking about computer graphics applications and systems. But I can already tell you that there is a theory which is called the tri-stimulus theory, which tells you that every possible color on the visible spectrum could be in some way obtained by the sum of 3 stimuli, of 3 base frequencies. These base frequencies are related to 3 specific colors, which are called the primaries, the primary colors.
From this I mean that you choose 3 primary colors. You can combine these 3 primary colors and obtain other colors. The 3 primary colors that you choose determine the gamut of the colors you can get. That is, the area of colors that you can get. So RGB, for example, are 3 primary colors that allow you to get millions of colors, not everything which is visible, but a satisfying range of colors. If you mix together red and green, you get yellow. Red and blue, you get violet. Green and blue, you get cyan. If you mix everything together, you get white. White, as the sum of all the primary colors, is the color which bears the most energy, as the sum of the energy in red, the energy in green, and the energy in blue. Black is the absence of energy, which is no color. There is no source emitting red, green, or blue. So if you want to make black, we will have 0 emission of the channel of red, 0 emission in the channel of blue, 0 emission in the channel of green. If you want to make white, then that will be the maximum energy, which will be the maximum emission on all 3 primary colors, so on red, on green, on blue, to get white. How do I represent the quantity of energy which I am emitting on each channel? I usually use the letter I, and since every light emission is emitting some quantity on the red channel, some quantity on the green channel, some quantity on the blue channel, every intensity of every light source can be represented with a vector of 3 elements. The first element is the intensity of the red channel, the second the intensity of the blue, and the third the intensity of the green channel. Please do not mix up these vectors with vectors used for points and directions. Okay? This specific vector doesn't have a 4th coordinate 0 or 1, right? Because I've seen things during my career. So this is not a point, this is not a direction, this is an intensity. As such, it does not have a 4th coordinate, nor 0, nor 1, nor 12. Okay? Good. It's just red, green, and blue put together in one. This is a little bit of tristimulus algebra. If you have 2 sources, A and B, with 2 vector intensities, they could be summed together, because lights sum together, like this, IA plus IB. Or you can modulate one color, like this, IA multiplied by IB. When do you modulate the color? Well, you make a luminance composition using a sum when there are 2 light sources. For example, you are at a disco dancing, and there are 3 lights, red, green, and blue. If you were to shine these 3 lights over the same spot, I don't know, there is a girl dancing, then you put the red light on her, then the green light on her, then the blue light on her, then you will see her white. That would be luminance composition. Okay? So you sum together 3 light sources. Modulation is used in computer graphics when you're summing the color of a material with the color of a texture. For example, you have a red object and you put over it a texture with yellow things. What actually comes out that the color of the texture gets modulated with the color of the object. This modulation is calculated like this. When texture are present, the resulting color derives from the color modulation between the color obtained by luminance composition of each channel. So, if you have a red object and a yellow texture over it, and a shine, and lights will shine over it, the color that you get depends from the luminance given by the texture and the color of the object. Okay, we have seen that we have luminance and that we indicate it as IR, IG, IB. What are the values that we can put? What are the numbers that we can put inside here? The surface intensity, I, in an illumination model, usually has a value in a range from 0, 0 to 1, 0. Which means, in theory, that you can have an infinite number of intermediate values within this range. Which is okay in theory, even if in practice, what happens that a given computer graphics system would only display a limited set of intensities. By computer graphics system, I mean the combination of a video board with its monitor, for example, or its beamer. So it really depends from the video board, but also from the monitor, how and which is the precision with which such intensities are represented on the monitor. This is one complication that it's difficult to express in an absolute way intensities, because we are bound to create these intensities on a monitor, let's say for simplicity, that we don't know in advance. And every monitor has intensity characteristics which are different. It also, maybe even if it's the same model, but one which is just out from the factory, and another which has been used for years. Even if it's the same model, they will show differences in the way they show color. That's one problem. The other problem is the way we perceive color. We perceive color in a logarithmic fashion. What does it mean? It means that when intensities are very low, so dark colors or not very brilliant colors, even a small intensity difference in numbers is visually perceived like a big difference. But as soon as the intensity builds up, so I go to very high color intensities, even if there is a big difference in the emission of light, I don't see it. So, for example, if I'm in the dark and somebody lights a very feeble light, I see a big difference from dark to the feeble light. But if I'm staring at the sun, and the sun at some point changes its intensities even of a very big quantity, I almost don't see any difference, or I don't see any difference. Okay? So the way I perceive is related to the area in which I am looking. So it's not the absolute quantity, the absolute distance. I mean, from 0.01 to 0.02, I see low intensity, I see a big difference. But between 0.98 and 0.99, I don't see any difference, even if in absolute I have the same distance. Because my eyes work in a logarithmic way. So they see a direct proportionality in the low intensity. In the high intensity, they sort of saturate. So they are not able to see differences anymore. So what happens is that actually, if we take two intensity values as a ratio, we perceive the difference to be the same only if the ratio between the two intensities is the same, but not its distance, its absolute distance. As an example, we perceive the difference between intensity 0.20 and 0.22
as the same as the difference between 0.80 and 0.88. So you see, it's a much higher intensity, but it's a much bigger difference, but since it's a higher intensity, we need more energy to have the user, to have the viewer see the same difference. That's another problem, logarithmic perception. So, it's just the ratio between intensity that gives us the same perceptual difference. So, R, the perceptual scale, the perceptual difference that we can represent with our device, is actually dependent from the ratio of all the possible steps of intensity. So this is the first step of intensity that our graphic system is capable of. This is the second, the third, the fourth, and so on. Therefore, in general, I can express any intermediate intensity like this. Step k of intensity of my graphical system depends from the general ratio of each step elevated to k, starting from the lowest intensity that my graphical system is capable of. If I know how many degrees of intensity I can represent with my graphical system, then I can calculate what is my step between intensity, R. For example, in a grayscale display with 8 bits per pixel, n equals 255. Usually, a monitor, did you ever try to look at a monitor which is black? It's not actually black. Did you ever try to watch it with all the lights off? You will see that it's not black, but actually there is light in it. So, that light, when it is completely black, which is not pitch black, is the minimum intensity. So it's not 0, 0, because you yourself see that it is very dark gray with some light in it. That is Y0. So, for example, 0.01. Using this formula, you can calculate if the ratio of successive intensity is this one, what is the actual value for the 256 intensities of the system. So I can be 0.01, 0.102, etc., 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 up to 1. Why do we need this? Because this will be the relationship between the RGB values and the intensity. Since all the lighting models are dealing with intensities, after that we have the intensity, we have this number. But from this number, we have to determine the level of red, the level of green, the level of blue. So we work out the intensity, and from that, we work out the step from 0 to 255 of red, green, and blue. This is why we need this. And this is how we do it. We go from the intensity to the luminance level in RGB. So it is 0 red, 250 green, 255 blue. We do it like this. We just invert that this relationship using a logarithm, and we can find, given the intensity, for example, on the blue channel, what is the step number for the blue channel that we need to get that intensity. Over here, K. So it will be, for example, 32, or 0, or 255. Okay? That will be the value level for red, for green, or for blue. So, my Fung model will give us I, which is the intensity of light. But from the intensity of light, I have to calculate which is the quantum step from 0 to 255 that my graphical system uses to represent that intensity. So I work it back like this, which is K. Okay? So you will use Phong model to get the intensity. The intensity from the Phong model is not enough. You cannot pass to your video board the intensity. The video board needs to know a number from 0 to 255 for red. Same thing for green, same thing for blue. So you have to pass from the intensity value to the quantum step in a 24-bit system for each one of the channels. And this is the way to do it. This is an exercise. Get the RGB color that has an intensity of red 0.456, an intensity of blue 0.035, and intensity of green 0.803. Calculate the RGB levels that you need for visualize light with those intensities. You have to know that your frame buffer has a depth of 24 bits, so it means that every channel goes from 0 to 255. You have to know that your monitor is a fairly good one, so the lowest luminance value is 0.01. This is a parameter from the factory. If you go to the manual, there is several data in your monitor manual. One of these is the lowest intensity value. And this is what to do, how you do it. So it turns out that, for example, the K for the red is 212.347. For green is 243, for blue is 69. So in general, the answer is 212, 244, 70. Okay. Okay, we have classified materials. We need, before starting going on with our illumination model, we also need to classify light sources. Light sources, well, it's like a lamp, the sun, or something that generates illumination, light emission. There are basically 4 types of light sources: ambient light, point sources, spotlights, distant lights. Ambient light. For every light, before showing you the different ways that we represent in vector form the different light sources, I have to tell you that we consider actually that each light source emits with different components. Okay, RGB, we already seen, are the components of the emitted light. But the source itself can be represented by this matrix L. This matrix L is used together with a set of coefficients, which are called attenuation coefficients, to give you what is the intensity of light which is actually emitted. So I is the energy that comes out. But R and L are 2 factors which contribute to make that quantity of energy coming out. R, it's very simple. It's a coefficient, so it goes from 0 to 1. And you have 1 coefficient for each channel, red, green, blue. So if you have that the coefficient of attenuation for the red is 0, it means that you are not emitting anything over red, and so on. The other interesting thing is that this is the property of the light. The property of the light depends from each one of the color channels. So you have red, green, and blue. And then you specify how this light interacts with within an ambient context, within a diffuse context, and within a specular context. This is actually counterintuitive. It has not to do with the physics anymore. It's already part of our computer graphics model. When you specify in computer graphics a light, you're already specifying, setting up the light, explaining how this light will behave when it will encounter, for example, a diffuse material in the area of green. So GD, green diffuse. You will explain how it will behave with a specular material in the green, or with a specular material in the red, or in the ambient context with the red. So it's actually something very strange, because you're specifying in the light source how the light source behave with diffuse, specular, or ambient point sources and materials. I can make myself more clear if we look together at an example. This is one of Nate Robbins' tutors that you have available for download from my page, I believe. But if they are not there, you just can Google Nate Robbins. Nate Robbins is written like this. Oi. Fuck. I lost it. Okay, never mind. Jeez. Okay, so you just Google for this, OpenGL, tutors, you can find them, but I believe there is a link in my page as well. This is one of them. The tutors are nice because, well, they're open source, so you can see how Nate wrote them. They also give you a few examples of the foundation of computer graphics. And this specific tutor over here actually is very useful to explain how we model light sources and material. Look, over here there is the L matrix, except for this column over here, which is the alpha channel, which is transparency. So just ignore this. But you see, it's here. This three over here is actually the matrix that I was talking about earlier. This one. Okay, made a mess. This one over here, right? Here in the light source, you're specifying what is the behavior of the light source for the ambient light, for red, for green, and for blue. This is for diffuse material, for red, for green, and for blue. This is for specular material, for red, for green, and for blue. So this is the light. This is for the material. For the material, still don't look at the last column, which is the alpha channel, that is transparency. We don't consider that for the moment. You say what is the coefficient of absorption. This is the R that I was telling you in that formula. E equals R multiplied by L. The absorption for red, for green, and for blue in ambient. The absorption for red, green, and blue in diffuse. The absorption for red, green, and blue in specular. This one over here is a contribution of self-emission. That is, the object itself emits light from its inside. It's zero now. We don't consider this. This one is a parameter which is called shininess. It tells you how much similar to a mirror or to a metallic object the material is. We will come to that.
Now look. Now I'm going to tell that this material not to consider any absorption in the ambient, not to consider any absorption in the diffuse, not to consider any absorption in the specular. So, as a result, the object is completely black. Okay? Because every color which is emitted by the light source, which is over here, is actually nullified by the fact that you have 0 in all the coefficients. Now I'm putting to 0 also the light source. So we will have a black light source emitting no light over a black object. So now it's pitch dark, right? This over here is just for moving the light source, so we don't. It's actually not very interesting. Now, let's start from one simple thing. Let's say I want my light to emit the maximum quantity of energy, 1, this is the intensity, over the red channel in the specular material. So this will be LRS, that is emission in the red for the specular part. So now the light is completely red and made for specular objects. Why do I steal the object black? Because still I have to set my R matrix, which is the material coefficients. Now I'm going to say that for the red, this material has a coefficient of 1, which means everything which comes in equals to everything which comes out. So maximum reflection for the red specular. Okay? What do you have? You have an object which is very metallic and very red. Do you want it a little bit less red? I can say only half of the red which is coming in will go through. So you see, it's not as red as before because half of it is absorbed and half of it is reflected. Why? Not because I've changed the light, but because I changed the property of the materials for the red, for the specular part. Now let's do it again, but with the diffuse part. I'm saying I'm emitting completely, let's change color, completely green for the diffuse part, still black. If I said, like I said before, but use a 1 coefficient for the red specular, which will be the color? Will still be black. Why? Because the light is emitting completely green diffuse, and the material is such that it emits back only completely red specular. So even if there is a green diffuse light shining on it, the object is still black because the material of which it is made only for reflecting at 100% red specular. To make it completely green, I have to tell that the material reflects completely the green diffuse. You see? Also notice that the appearance of the donut is different. Well, that's a donut, but you don't eat it. You need sugar on it. Look at the highlight areas. Do you see how they are more diffuse? Look, these are like they are like this in the diffuse light. Now let's do the same thing, but with the specular, the green specular. We should see a difference. You see the difference? This is much more specular. It's like the light is not diffuse, but it's concentrated in much more narrow areas. Why? Because this now is a specular material. It doesn't diffuse. It concentrates its reflection in narrow angles. And this is the result. Some areas are very bright, some areas are very dark. Why? Because all the energy of the light gets concentrated in small areas.
in this way, you have some parts that are very bright and some parts which are very dark, because the quantity of energy is the same, but it gets more concentrated in smaller areas. This means that you have darker areas and brighter areas. If you don't do specular, but if you do diffuse, then you have the same quantity of energy, but more diffuse over the whole object. So you have less dark area and less light areas, more diffuse. Do you follow me? Now, it's up to you and your creativity to mix all these parameters in order to get the best effect you want. Now, you can even mix a material which is partly diffuse and partly specular. Why would you want to do that? Well, you see for yourself that if you go for completely specular, oops, this is self-emission, I'm sorry. If you go completely specular, maybe this is not what you want. Well, you want it to be metallic, but there is too much dark areas. This is not actually what you have in mind. Then, to attenuate a little bit the effect, you could put in a little bit of diffuse light. Well, let's put diffuse light over it, and you see that now it has very bright areas because of the specular part, but the areas that were dark before now are a little bit more colored because of the diffuse part. I don't like the effect is too much flat. Well, I can maybe turn down a little bit the coefficient of absorption, which absorbs only the diffuse part. You see? And I can really modulate the quantity that I think best for my specific see. So, I can really, this is the beauty of it. Of course, it has not much to do with the real physics of the problem, because any light source doesn't give a damn about the fact that it's shining on a specular or on a diffuse material. This depends entirely from the material in real physics. But in computer graphics, you can mix, you can really set up the light source by putting also its emission characteristics, subdividing them according to specific materials you want it to interact with. And of course you can combine colors. So you want to do something a little bit more no, it's the other one, a little bit more yellowish or bluish. You can now I added to the green I added the blue, and you see that I'm going a little bit more bluish, but change a little bit so you can mix. You don't see it very well here, but here you see it very well. Okay, you can try for yourself, try and experiment. Download the tutors and try to mix up a little bit. Try and understand the relationship between the L matrix over here and the R matrix over here. The L is the matrix of emission, and the R over here is the matrix of the absorption at the material. Last thing is about shininess. I think you can see it better if I put back everything to just let's give it here shininess. No, this is self-emission. Sorry, shininess. Okay. If I put shininess to a bigger level, what do? I enhance the concentration of light on the object. So all the light will concentrate in very small areas. If I put the shininess low, then all the light will distribute in very wide areas. So of course, if you exaggerate, you will have effects which are not really interesting. But if you modulate in between, you can really modulate the dimension of your highlights. Okay? Okay, that's it. Right. So now you understand why we make a difference over here and why we use two terms over here to determine the intensity of light which is shining on specific objects. This is the slide I was looking for before. Okay, I'd say that it's enough for today. Next time we will see the point sources, and we will start with the Phong illumination model, which is the model, the most important model to compute color geometrically in computer graphs. So very important. Don't miss next lecture. So thank you very much. Have a good evening. Have a good weekend. Bye-bye. Yes, because there are 3 channels. So you need 8 bits for red, 8 bits for green, 8 bits for blue. So it's 24. But the level for each channel is 8 bit, so it's 255. Ho visto che hai preso appuntamento, bravo. I see that you made an appointment with Christian. Okay. You go then, you tell me what... Don't let yourself be scared off. They have skeletons and bones over there. They do strange things. But it's interesting in my opinion. Okay. Write to me. Okay. Bye-bye. Have a good weekend. Ciao.